I want to begin by writing an expression that is in factored form. So I'm going to say this is like point A, and I'm eventually going to progress to a point B. And so at point A, I'm going to start with this expression that I said was going to be something that's in factored form. I'm going to write it as the product of the factor x plus 2 with the factor x plus 4. And then I'll just kind of make a note that right here, this is an expression that is considered in a factored form, right? Because to be factored means you write an expression as a product of factors. Here are a couple factors, x plus 2 and x plus 4. So what I'm going to do to go from point A to point B is I'm going to multiply the factor x plus 2 with the factor x plus 4. In other words, this is going to expand the expression, also get it into a simplest form. So I will work my way to something that is in a simplified form once I get to point B. So to multiply this out, of course, we can just use the FOIL method to multiply these two binomials with one another. So we're going to get x squared and then plus 4x and plus 2x and then plus 8. We'll recognize that the 4x and the 2x are like terms with one another, so that's going to simplify all the way down to x squared plus 6x plus 8 as a final simplified form there at point B. Now, what I want you to recognize from this here is if I call this kind of lowercase a, this 6 right here, lowercase b, and this 8 here, lowercase c, those are like the coefficients of the individual terms, you're going to notice that this b value, this coefficient of the x, 6, actually does come from the sum of the 2 and the 4 right there. And then also this h, once we had FOILed the expression, came from the product of the 2 and the 4. And you can actually kind of see this generally like work out. So if I just had a very general expression like x plus a number p, and then x plus a number q. Now q might be different than p, but it could be allowed to be the same number as p. And if you FOIL that expression out, you're going to see that you're going to get x squared, and then you're also going to get the number q times x, but then you're also going to get the number p times x. So I put them in that same blue, darker blue color there because they're going to be like terms. And then finally, p times q is going to be plus PQ, and then when I combine those darker blue colors together, you're going to get whatever P plus Q is as an answer times X, and then plus P times Q. So you can see, similarly, like the P and the Q, that's the sum of those two numbers right there, and then the n term, that constant PQ, came from the product of the P and the Q, similar to how we had the sum of the 2 and the 4 and the product of the 2 and the 4. So that's useful relationships for us to recognize, because as we're about to move into now here, a one-word instruction that we've seen previously is to factor an expression. Now previously, when we've dealt with factoring of expressions, we've worked to identify a greatest common factor of all of the terms and factored that GCF out. With these examples here, we're not going to see that. So like if you look at this first example, for example, there's no number nor variable that they have in common. So there's not going to be a GCF to factor out, but you're going to notice that the expression is of the form some number times x squared plus another number times x plus a number. And when we have expressions of that form, we should be able to kind of go from where we're at right now at a point B to a point A. And when we go from point B to point A, it's the opposite of multiplying, which means that when we go from point B to point A, we're actually trying to factor the expression. And so recognizing the relationships that I was just alluding to earlier about the relationships between P and Q is really important for us. So it does turn out that when I try to factor this x squared plus 10x plus 24, what I'm really going to try to do here is try to unfoil it, basically. And so like if we think about foiling, clearly x times x is going to have to give you the x squared. Now since everything here is positive, we know that we're going to have positives right here. Now, like, this is just going to be a number, right? And this is just going to be a number, right? And we know that directly those two numbers, P and Q, if we can call them, should multiply directly to equal 24. It's just that to get like this 10x, right, that's actually going to come from combining the product of those two things with the product of those two things, right? So like the two blue things add together to equal the 10, really, but the two numbers should multiply to equal 24. So in terms of actually figuring out what these unknown numbers here should be, we really want to look for numbers that multiply to 24 but that are going to add to 10. So really we can kind of limit our choices to these numbers: 1 and 24, 2 and 12, 3 and 8, and 6 and 4, because those are the only integers that multiply to equal 24. But if we add them together, here we get 25, here we get 14, here we get 11, and here we get 10. And what we want to add to is we want to add to 10, right? So the only choice that's really going to work is to use x plus 6 and x plus 4. And it turns out that this expression is a factored expression, but it is equal to this expression right here. Because if you think about foiling out that expression, it will simplify to x squared plus 10x plus 24. If you wrote your answer as x plus 4 times the factor x plus 6, that is also the correct answer, because we know that x plus 6 times x plus 4 is the same thing as x plus 4 times x plus 6, because multiplication is commutative, right? So like a times b is always equal to b times a when we're dealing with real numbers. So moving over to the example right next door, I made sure that everything here was also positive. So there is no GCF acknowledging that fact, first of all. So if we're to factor this, we can write a first factor with an a plus something and then an a plus something. So these two numbers, whatever they are going to be, definitely have to multiply directly to equal the constant, the 36. So that means we're going to be limited to like 1 times 36 and other things that multiply to equal 36. So 2 times 18, 3 times 12, 4 times 9, and 6 times 6 are our options. We want to try to find the options that are also going to add to be a positive 15, and the only option among those factor pairs would be 3 and 12. So therefore, a plus 3 times a plus 12 is going to give us the factored form of that expression. So in the next little section, I made these two examples similar to each other, but they're different from the previous two examples, because what I have is I have the b value, so the coefficient of the kind of middle term is negative, but then all of the other terms are all positive. So it turns out that when we have this case, you should kind of know some for certain things about the factoring of this. So with this first example right here, there is no GCF of all of the terms. So if I'm going to try to factor this, I'm going to have a first factor with a q something and then a q something, right? Now here's the deal, is that in order for this to be negative, but then for that last number to be positive, the only way we can get this to factor is if both of these numbers that follow the q's are negatives, because you're going to multiply the negative with the negative to give you the 18 directly, but then the two negative numbers are going to have to add to equal negative 9. So when I list out these possible factor pairs, I'm going to write them as both negatives, because negative 1 times negative 18 will give you positive 18. But when you add them, you get negative 19, and that's not what we want, because we want to add to negative 9. So I need to keep thinking about other factor pairs. That adds to negative 11. We also have negative 3 times negative 6 is positive 18. That will add to negative 9, right? Because negative 3 plus negative 6 is negative 9. So it does turn out that if you do FOIL out q minus 3 with q minus 6, it will simplify to q squared minus 9q plus 18. So q minus 3 times q minus 6 is the factored form of that particular expression. So right next door, you see the same sort of scenario where the last number is a positive, but the middle term is a negative. So that should automatically clue you into the fact that this should have to be m minus and m minus. So both of those are going to have to be minus signs there. So you just have to find the pair of numbers that are going to multiply to be 100, but add to negative 25. It does turn out that negative 20 and negative 5 do multiply to equal positive 100, but are going to add to negative 25. So it does turn out that m minus 5 times m minus 20 is going to be the factored form of that expression. And then these examples down here, they are all similar to one another in that the last number, so the constant term, is a negative, and there's really only one way that you can get that to happen, and that's if, like for this very first example right here, where you have positive w times positive w, of course, to give you w squared, then the only way you can multiply to equal a negative 12 directly is if you have one positive and one negative. So in this particular scenario, then, we want to multiply directly to equal a negative 12, right? But then add to a 4. So you're going to have quite a few options, because you could do 1 times negative 12, but you could also do negative 1 times 12. So you're going to kind of have like 2 options for each pair of numbers, right, depending on which one you make negative. So the same thing would be like 2 and negative 6, or you could do negative 2 and 6, or 3 and negative 4, or negative 4 and 3. So of those, you have to find the one that adds to positive 4. So you're going to kind of have to limit yourself to probably these 2 options, but in the first pair, that actually adds to negative 4, and this adds to positive 4, and that's the option that you would want to have. So you'd have to have the 2 be negative, which means that I'd have to have a w minus 2 and then a w plus 6. Okay, and you can check, like, if you FOILed that expression out, it needs to exactly equal w squared plus 4w minus 12. And if you take the time to do so, you'll verify that definitely it works as such. With the next one, it also ends with a negative 12, right? But that doesn't mean that we necessarily need to use like 6 and 2 again. So because what we have in the middle there is we have a negative 1r. So it, based on our factor pairs that we had earlier, this would actually be like the factor pair that we'd want. We'd want a little bit more negative, the 4 to be negative, and then the 3 to be positive, so that when we FOIL that out, then we're going to simplify to a negative r in the middle, but then still end with that negative 12 at the very end. So with these other last couple examples right here, just kind of breezing through these, we know that because the last term there is a negative, one's going to have to be a plus and the other's going to have to be a minus. In order to get a negative 31, you're really going to have like subtract 32, and then we know that negative 32 can times with a positive 1. And then also negative 32 plus 1 is negative 31, right? So that's going to give you that factored there. And then finally for the last one right there, you're going to have t and t. You're definitely going to have a positive and a negative to multiply to equal a negative 63, but then you also need to make sure that you combine to equal a positive 2. It does turn out that if you have a 9 and a 7, they're 2 apart from each other, you would need more positives, so you'd need to make the 9 the positive and then the 7 negative there. Alright, so there's a good number of examples of factoring expressions that are kind of that standard form where you've got a squared term and then a linear term in the middle and then that constant term at the end. So as we jump to these couple examples right here, we can see that this expression is of the same sort of form that we've just been working with. So when we try to factor this, we'll recognize that there is positive, but we've got a negative middle. So the only way we could factor this is by making both of those be minuses to multiply to equal the positive, but add to a negative, right? So of your options, you've got 1 and negative 1 and negative 15, or negative 3 and negative 5 can multiply to equal that 15, right? But when you add those two, you're going to get negative 16, and when you add those two, you're going to get negative 8, none of which add to negative 3. So you're out of options, right? Like, so what numbers can we actually put right there to get that factored? Not whole numbers, right? Not integers, at least. So it does turn out that if we were to try to just restrict ourselves to just whole numbers or just integers, we're actually not able to get this expression factored using only whole numbers or integers. So what we're going to say for now is that that expression is actually not factorable in the integers or just using integers. So what we can usually say about that then is if it's not factorable in the integers is that we could also just say that the expression is prime. So we'll see the same thing actually with the example right next door right here. and that it will be prime. Now, if we were to try to factor it first, because you won't know it's prime until like you've exhausted all your possibilities, right? We'll acknowledge the fact that we want to multiply to equal a negative 27 directly. So we're definitely going to have a plus and a minus. So you'd have to think about, okay, 9 times 3 or 1 times 27, that's it, right? So how would you get one of them to be positive and one to be negative and then add to a positive 12? Well, it seems promising with 9 and 3, but if one has to be negative and one has to be positive, they're going to add to either 6 or negative 6, not to a 12, right? So then clearly that's not going to work. So that exhausts all your possibilities. So same thing's happening right here, in that you just have really a prime expression with the y squared plus 12y minus 27. And so then just from here, we're just going to kind of look at some other special cases going on right here. So if you look at the examples that are here, p squared minus 144 and x squared minus 9 and 100 minus t squared, these are kind of special cases because they're all missing the middle variable term, right? So like this doesn't have the middle p to the first power term, and this doesn't have the x to the first power term, that sort of thing. And there's also all kind of subtraction happening with all of these. And so what you'll kind of recognize is that we can eliminate a middle term whenever you FOIL out, let's say, I don't know, like x plus 6 with x minus the same number, because when you do FOIL that out, you get your x squared, but what'll happen is you'll get a subtraction of 6 and then also an adding of 6x, but then that's going to equal 0, right? So they just kind of cancel each other out, and then 6 times negative 6 is minus 36. And so what you'll see there is then, okay, if I just have x squared and then minus some other like number, right? That's kind of how we can kind of eliminate terms. And so that's the pattern that we're seeing with these examples right here. So to factor p squared minus 144, we want to write it as a product of factors. And so what we can do is we can say, okay, well, we can do p times p, and then to get 144, we can recognize, well, it is 12 times 12, right? But we can eliminate the middle terms if, for one hand, we do a plus 12p, but then we also do a minus of 12p, that can eliminate them, right? So it does turn out that factoring this expression, we can factor it as p plus 12 times p minus 12. Right next door, it's basically the same thing. You're going to have x minus 3 and x plus 3, since 3 times negative 3 will give you the negative 9. And of course, you eliminate the middle terms by combining negative 3x with positive 3x. With the last example, you probably don't want to start with like t and t, because like t times t equals t squared, but we want negative t squared, right? So we can, for this particular one, think, okay, well, if we do 10 times 10, that's going to be 100, and then I can eliminate any middle terms if I do a plus 10t, but then also do a minus 10t, right? And then we can see that the negative t will multiply with a positive t to give you the subtraction of t squared. So that gives you a factored form there. Now, giving a little bit of terminology to what we're seeing right here, what you're seeing like in these sorts of expressions is that x squared is a square, as well as what you see right there. And when you think about what a square is, or a perfect square is, it's the same thing times the same thing, right? 1, 4, 9, 16, 25, 36, 49, etc. They're all perfect squares. And that's exactly what x squared is, because it's x times x. And that's exactly what 36 is it's 6 times 6. And what we're seeing is that we're subtracting, and any subtraction is always called a difference. So what we're seeing whenever we see this, or we see this, or we see this, is we call those differences of squares. A difference of perfect squares. And so in general, whenever we have a difference of squares, we kind of have this kind of special factoring going on. And so in general, whenever you have something squared minus something else squared, it always does factor as the following. Take a moment to think about what I just wrote in the blue there, right? If you have something that's a squared minus b squared, it is a plus b times a minus b. What do I mean by that? So if I have, let's say, x squared minus 49, but I treat that as like x to the second minus 7 to the second, because that's exactly what it is, then if I use that x and that 7, then really I can do an x plus 7 and an x minus 7, and those would be the factors that I would use to factor that expression. Okay? okay? So that special factoring of difference of squares is something that we're going to see a lot, and we'll dive into. So that's a little bit of exposure into that realm. Some other special cases that you might see is when we have like x plus 4 times x plus 4. Meaning that I'm taking the same thing times the same thing, and whenever you do such a thing, when you FOIL that, you get x squared plus 4x plus 4x. So really you just kind of double the 4, but then 4 times 4 is really going to give you a perfect square at the end that you see right there, right? So we're going to see these sorts of special cases here, where like, for example, right here, you can see that 36 is 6 times 6, but then this right here is 6 plus 6. So it does turn out that this does factor as exactly x plus 6 times x plus 6. Now, here's the thing, is that you really shouldn't leave it as just x plus 6 times x plus 6 when they're the same factors, because if I called this here y and I called this here y, basically you've wrote an answer that's y times y. But can you simplify y times y? Yeah, it's y squared, right? So in math, whenever you have the same quantity times the same quantity, you can simplify that. So it does turn out that this is the same thing as the quantity of x plus 6 times itself. So it is the same thing as the quantity of x plus 6 squared. With the next example, if you were to get this factor and you're just trying to like guess and check this, you can do b times b. Now, if you've got a positive 4 at the end but negative in the middle, you do know you have to have negatives there. And if you did like 1 times 4 or 2 times 2, that can give you that 4 there. But it turns out, right, that you would want negative 2 and negative 2, because then you would get negative 2b minus 2b to give you the negative 4b in the middle. So lo and behold, you get another example where you have b minus 2 times the same b minus 2. So it's going to end up being b minus 2 squared. The last example, if you want to work it out on your own, you can. It ultimately does boil down to be w minus 13, that quantity itself, all squared. So putting a little bit of terminology to this right here, you can see that whenever you take the same thing times the same thing, right, you actually get a perfect square. So for example, like when you do 4 times 4, right, you get 16, which we do call a perfect square. So if right here we're taking the same thing times the same thing, then right here, this is just kind of an algebraic version of what we would call a perfect square, because it's the result of taking the same thing times the same thing. Now, because that there has 3 terms, it's also a trinomial, so that is a perfect square trinomial that you're seeing there. We'll get more into talking about perfect square trinomials in depth as we continue with algebra later on. And then finally, kind of one last example that you're going to see with some special cases right here is that these have missing C terms, right? They have no constant at the end. So it does turn out that if you just have like only variable terms, no constants, try to find a GCF. And like for the first one right there, they have an R in common, I guess. You could factor out an R, and then you just have like r times r plus 8, right? If you think like, okay, distributing, yeah, it works out. And that actually is factored because it writes it as that factor times that other factor right there. So similarly with the other example, u squared minus u, it doesn't have any other constant, but they both share a u as a common factor. So if you did factor out a u, you'd have u times u minus the number 1, right? And that would also be an appropriate factored version that you see going on there. Just to kind of help you relate this to the other examples we were seeing, it does kind of fit nicely with what we were seeing before, because if I treated this first example, r squared plus 8r, but then plus 0, right? When we think about then trying to factor this expression, don't we want these two numbers right here to be numbers that multiply to equal this last number of 0, right? But then also add to equal this number right here of positive 8. And if you think about two numbers that are going to multiply to equal 0, but then add to 8, it turns out that 8 and 0 are two numbers that you can multiply to equal 0, right? And also add to 8. So if you factor this as r plus 0 times r plus 8, that would give you a factored form that looks pretty much like what we were doing before, but then you would recognize that right there, anything plus 0 is just the same thing you had, right? So that just simplifies to r, and then to r plus 8, which is what we saw up here, right? So it just relates it and shows you kind of that it fits in the same relationship that we were seeing with the trinomials previously.